Okay, got a couple more related rate problems for you here. This is one of my favorites. I made this one up a number of years ago. You've got a child who's flying a kite, and they start off with a kite parallel to the ground and right in their hand, and they start letting out the string at 10 feet per second, and also they notice that the height is rising, the angle is increasing at a rate of pi over 60 radians per second. So two things are happening. If I want to do it from this side, the string is coming out farther and farther, and the angle of elevation is increasing. So both of those things are going to make the kite go higher in the sky, and we want to know how fast is the kite gaining height at 20 seconds, okay? T equal to 20. So let's go through the steps and remember what they are. The first one is, what do we want? What is the rate that we want? And in this case, we want the rate at which it's gaining height. So let's let h stand for the height. Okay, so in this case, then we want dh dt. Okay, dh dt. 2. What is it you know? Well, we know two rates. We know the rate at which the string is being let out, this length right here. Let's let this stand for L, for the length of the string. So we know that dl dt is equal to 10. And we also know that the angle is called the angle theta, is changing at a rate of pi over 60 radians per second. Okay, so notice that in order to do these problems, you need to assign variables to these things. You're not told that in advance. You have to decide which things you need to assign variables to. I sometimes tell my students that the Genesis of the Old Testament of the Bible starts off with God saying, "Let there be light," and "Let there be animals and plants," and so on. And with all these lets, the story goes that these things all appeared. And then I tell my students, okay, now watch my hand as I say, "Let there appear a ping pong ball." And I put my arm like this, and I say, "Let there appear a ping pong ball." And they're kind of waiting for something. Nothing happens. To which I say, I don't have any power over the physical world like that at all, except I can raise my hand up and down. That's kind of cool. But otherwise, I can't just let something exist which come out of nothing. But you can do that in the world of math. That's kind of cool. So we have the power to say, let there be this angle, this variable, this one, and this one. And so take full advantage of your power over the world of ideas in mathematics. Okay, you've got the power there. So anyway, there's what you know. The third thing, what's the relationship between these three things? Okay, so there's where you need to, again, know it has nothing to do with calculus, but it does have a lot to do with trigonometry. Recall from what we said earlier that the sine is equal to, the sine of an angle is equal to the opposite over the hypotenuse. That's really what it amounted to when we did the unit circle. You had the opposite here, and the hypotenuse was right there. And so this over this was the sine of the angle. And similarly, here's what we've got. And so I can say h of t is equal to L of t times sine of theta of t. Okay, let me explain that one more time. I know that h over L is equal to sine theta, and so h is equal to L sine theta. After you worked with trig long enough, you can just see it right in your head. So there it is right there. Now, let me make another point. I could have written it like that, and then we could have taken the derivative of both sides. What's the advantage of writing it like this? Two advantages. One is I would prefer using the product rule than using the quotient rule. Okay, just a little bit easier, no denominators to worry about. So there's one advantage. The other advantage is this thing is already set up then to give me the answer, because what I want is dh dt. So a whole lot of advantages from going ahead and multiplying this through and writing it in this form. So we have that. Now what's the fourth step? Differentiate. So we get dH dt is equal to, notice we're going to have to use the product rule here. So it's going to be dl dt times the sine of theta plus L times, notice what we're going to have to do here. Work from the outside in. The derivative of the sine is the cosine of theta of t. I'm just going to write it as theta. Times the derivative of the inside. The derivative of theta is d theta dt. So those are all functions of t. So now we can finish. What's dH dt at time equal to 20? T equal to 20. Well, here's our dL dt, that's 10. Now we have the sine of theta. Oh boy, we got to think about this. This takes more work. We need to know what's the angle going to be when t is equal to 20. Well, think about it. The angle is growing at this many radians per second. And if you're doing it for 20 seconds, then it would be pi over 60. That's the rate times the time, gives you the total amount it's changed. So pi over 60 times 20 is 20 over 60, which is pi over 3. So that's the sine. Let's go ahead and figure out the whole thing. The sine of pi over 3 is equal to what? Use my unit circle here again. Here's pi over 3. That's the long one. That's square root of 3 over 2. So the sine of pi over 3 is the square root of 3 over 2. I'm going to put that in right here. Like so. Plus L. Well, the same thing. It grows at a rate of 10 feet per second, and it's doing that for 20 seconds. So 10 times 20 is going to be, it's going to have 200 feet out after 20 seconds. So it's going to be 200. Now it's the cosine of the same angle. What's the cosine of pi over 3? That's 1/2. So that's going to be 1/2. And then finally we have d theta dt, which is what? Pi over 60? Pi over 60. So now we just have a bunch of numbers to multiply together. What's that going to be? 10 over 2 is 5, so it's going to be 5 square root of 3 plus, let's see, 200 divided by 2 is 100. 100 divided by 60 is 5/3. So it's going to be plus 5/3 pi. Interesting. You wouldn't have come up with that as the exact answer if you hadn't had calculus. So there's your answer, and that's dH dt, so that would be in units of feet per second. So that's how fast the kite is growing. Okay, let's do another problem which is similar to this one. Another one I made up myself. I'm really proud of this one because it took a lot of time to figure it out so the numbers came out well. So see if you appreciate it. Okay, so here's the situation. You've got someone right here that's shooting an arrow up in the air at a rate of 182 feet per second. Shoots an arrow up. And someone right here has a camera, and the camera is rising in elevation. Obviously, it has to raise in elevation. The angle of elevation has to rise in order to keep the arrow in the lens of the camera in sight. And the question is, if this is 400 feet right here, here's the question. I've got it written down. At time equal to 2, what is d theta dt. In other words, how fast is the angle having to increase in order to keep that arrow in sight? And this is a very applied problem, because way back in '69, I think it was, when Neil Armstrong and Buzz Aldrin, is that his name, landed on the moon, then once they got on the moon, here was their Land Rover, like this, and then they set a camera. I guess for all practical purposes, the moon was pretty much flat. Okay, so they put a camera on the moon in order to be able to watch it when it took off. And of course, and this camera was being operated by someone at the Houston NASA headquarters in Houston, I guess it was. And so this person had to operate the camera so that it kept the lunar module in sight as it took off. And here's the problem. Light travels at roughly 186,000, actually 284 miles per second. Okay, I believe is the number. And the moon is about 250,000 miles from Earth. So in other words, even if you send a signal to this camera to start raising the camera up, it's going to take over a second, maybe roughly a second and a half, in order to get there. So the person down at Houston at NASA wasn't able to just watch this thing go and then raise the camera in sync with it. Instead, he had to anticipate where this thing would be a second and a half later. So he knew exactly when they were going to take off and exactly what the force was and so on, and how fast it would be rising. So given all these calculations, he just, without ever being able to see anything, he just started raising this camera, and it wasn't until later that they, sure enough, saw that, yep, it follows it up, and they could watch it go up. So there's a real life example where you need to be able to, in this case, get some sort of a computer or something to figure out what that angle of elevation should be. So anyway, that's kind of cool. So let's do this one. So here's what we want. We want d theta dt, and we want it at time equal to 2. Okay? What do we know? We know, should we call this h again? We know dh dt. What is dh dt? If you say 182, you're wrong. That's what I like this problem. It's the only problem I've ever seen. As I say, I developed it myself. I've never seen one in a textbook that does this. But it's the only one I've ever seen where the dh dt changes with time. Do you agree? This is the initial velocity of the arrow, but the acceleration on the moon, or in this case not on the moon, but on the Earth, the acceleration on the Earth due to gravity is going to cause it to slow down as it goes up. So this one requires you to remember from back, I don't know, about 5 or 6 lessons ago, that the height of an object under the influence of gravity is equal to -16t squared plus your initial velocity times t plus your initial height. So our initial height is 0, and our initial velocity is 182. So for our case, h of t is equal to -16t squared plus 182t. So there's the height, and we need dh dt. So dh dt is going to be what? -32t plus 182. So there's our dh dt. Okay? So that's what we know. Now we need a relationship between those. What's the relationship between theta and h? Well, we have that this is 400, and so let's see. What do we have? We have H over 400 is equal to, what is that? Let's see. Always go back. That's this one over this one. That's the sine over the cosine. That's the tangent. So that's the tangent. And so we have H over 400 is equal to tangent of theta, and might as well multiply through by the 400 right away. H of t is equal to 400 tangent of, I'll write it as theta of t. Okay? So there it is. And so now we can go ahead and take the derivative. And so if you take the derivative of both sides, what do we get? We get dH dt is equal to 400. Do you remember what the derivative of the tangent was? That was 1 over the cosine squared. So it's going to be 1 over cosine squared of theta, and then times the derivative of this, which is d theta dt. Okay? So now we can solve it for d theta dt, and I'm going to be running out of room here. I think I have room here. I'm going to get d theta dt is equal to, it's going to be cosine squared of theta dH dt, all divided by 400. Is that right? It's going to be cosine squared comes up times dH dt divided by 400. And finally, we want this at time equal to 2. So d theta dt at time equal to 2. Okay, let's figure it all out. First of all, what's dH dt going to be at time equal to 2? When t is equal to 2, it's going to be negative 64. 182 minus 64 is 118. So this is going to be 118 right here. Okay. Here's 400 down here. Now we need cosine of theta. Well, let's see. Cosine of theta. Cosine is this over this. This over this. Well, we don't know this length. We know this length. And using this formula, I guess we can find this length. Let's find it. What's h of 2? If you put in 2 in here, you're going to get 2 squared is 4. It's going to be negative 64. Sorry about this. I'm going to have to write it like this. Plus, here's your initial velocity, which is 182. 182 times 2. And that's going to be what? 182 times 2 is 4, 6, 364. So you add those together and you get exactly 300. Oh, how nice is that? So it turns out that at time equal to 2, using this formula right here for the h, at time equal to 2, this height is 300. And this one is 400. And so if you use Pythagorean's theorem, this is kind of a really nice situation. This is where it took a while to come up with these numbers just right. But if this is 3 and this is 4, you have 9 plus 16, if you square them, is equal to 25. So 3 squared plus 4 squared is equal to 5 squared. So that right there is a right triangle. And so if you make everything multiply it by 100, you got the same thing. So this is 300, this is 400, and so this is 500, which means that the cosine, what's the cosine? Cosine is 400 over 500, which is going to be 4/5. So it's going to be 4/5 quantity squared. So I guess you could play with that a little bit more if you wanted to, but I'm out of room, so I'll stop right there. So anyway, there's the answer. So very nice problem, I think, if I do say so myself, because it requires you to think about this, and you have to use this in order to get this height. So you have to put all that stuff to work. We'll stop right there.